get into solving the first question on our exam 2, mysterious quantum effects. So below I've got this signal of some mysterious quantum mechanical phenomenon. So energy versus time in seconds. Okay, so whenever I first see this, is this a periodic signal or is it just an aperiodic signal? Looks pretty aperiodic to me. So we start down here. So here, 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 here. So my full period, my t is going to be 29 seconds. So I know that my fundamental frequency, my delta F, is going to be 1 over 29. So I could start to kind of basically fill out kind of this problem. So, and then it's asking us to look at dominant frequency. So fundamental frequency, we've already solved that. We already defined the period here, t, up there. So let's go ahead and let's open up Mathematica and let's kind of start solving these problems. So this is kind of a nice way you could kind of, again, I could answer all of this question. I could answer most of this question. And only up to here, now I have to kind of, work and do my good old-fashioned, data analysis side of things. So let's pull up Mathematica. Let's open up a new worksheet. Ideally, again, you want to maybe have something prepared before the exam, but we could kind of solve this fresh. So we know that our t is equal to, capital T, is equal to 29 seconds. I know that my delta F is equal to 1 divided by 29. I'm going to work at my number of harmonics seems to be 5. So my maximum frequency, so F max equals how many number of harmonics? First 5. So it's going to be n times delta F, which is going to be here 5 times delta F, which is equal to 5 over 29. So I can kind of write that in there, delta F. So fund equals delta F. I know that my F max is equal to 5 times delta F. And voila, we've got those answers. So I know my fundamental frequency, maximum frequency, period. I've already answered quite a bit of this problem. But now we need to kind of go into the weeds, or not the weeds a little bit, but we need to start to kind of define and work with this kind of problem. So I'm going to actually, it's not really nice visually, but let's go ahead and write out our functions. So I know that from 0 to 7, my y sub 1 is going to be equal to 10. And here, this is going to be equal to, y sub 2 is equal to minus 10. Then I'm going to have to figure out this line between here and here, which I don't want to do because I don't want to do any math. I know that my y sub 4 is equal to, let's say that's about 20. And then here, my y sub 5, we're back to 10 equals 10. So I can go ahead and start to write out those values. So my y sub 1 is equal to 10. My y sub 2 is equal to minus 10. I also know that I have my fit. So my points here are at 10 seconds minus 10. And I want to find what is the function there that's connecting those 2 points at 20 and 20. And I could go from 1 to x. This is probably embarrassing. I should be able to do this, but I don't trust my math skills at all anymore. I'm so addicted to Mathematica. That's one of the hard things. Your GRE score is going to tank. But anyways, so there's my y sub 3. It's a lot quicker, huh? And then my y sub 4 is equal to 20. And then my y sub 5 is equal to 10. So that's my function. So I also have my, let's say, my int limits, my integration limits. So first, I'm going to go from 0 to 7. Then I'm going to go from 7 to 10. Then I'm going to go from 10 to 20. Then I'm going to go from 20 to 22. And finally, I'm going to go from 22 to 29. So there we go. Now, this looks like it might start to kind of continue, but again, from the signal that we're looking at, this is not periodic. This is an aperiodic signal. So we've got our period. So now I'm going to do my a sub n, which is going to be equal to my 2 divided by t times my integrate. I'm going to do this times integrate. Now I'm going to get my y. I'm going to make a little table. So, and actually almost made a huge mistake here, y sub 5. So my y funds are going to be equal to y1, y2, y3, y4, y5. So those are my functions. So integrate I'm going to make a little, it's always easier to just kind of do this step by step. It's a nice little teaching. And so I want to integrate my y funds 1, my first function, times cosine of 2 times pi times n times t divided by capital period from t goes from my first limits, so I could look over here, int limits 1, 1. So I want to go from here, from 0 to int limits 2, comma, int limits 2. So that code looks pretty good to me. Let's go ahead and int limits 2, close it up. Working on this here. So that's our first value here. So, but I'm going to do now a table function because I need to do this multiple times. I want to save time. So I'm going to go from I to I here to I here. I from 1 to length of, let's do y funds. And thinking. So, and then I want to do, because we need to add all these together, so I'm going to do total. I'm going to total these. And you can do this step by step again. You'll have enough time on the exam, but I just want to kind of, I'm always interested in making my code a little bit more efficient. So there we go. So cosine, there's my a sub n's. My b sub n's are going to be very, very similar, except for there's going to be a sign. And I need to rechange that variable, b sub n. I'm going to reevaluate here, a sub n. I know that sine of 0 is 0, but I could figure out my a sub naught, because I need to figure out my zeroth order harmonic. So my a sub 0 is the exact same thing, but cosine of 0 is 1. So I'm going to get rid of this and integrate here. I have a huge issue here because I see I have an x. I always make this mistake constantly. That's why you rerun your code. So actually, I'm going to go ahead and rerun this entirely. So I'm going to delete this right here. I'm going to quit my kernel, and then I'm going to do something I rarely do when I'm coding, which is evaluate the total notebook. So let me just do that right here. Evaluate notebook. Where are we at? Evaluate the entire notebook. Let's see if I get my thinking. This is a slower computer. On the other computer. Actually, I could do this on the other computer now, but I don't have my nice writing ability. Anyways, so let's go ahead and, so now I could do, I'm going to create a table because I know I'm going to eventually have to kind of figure out my dominant frequency. So we need to go from an to n goes to I, and then let's do a table. I'm going to call this my an's, which equal table. Switching goes from, oops, that's not good. I from 1 to 5. Do the same thing with bn's. My bn's, bn 1 to 5, and then I'm going to just go ahead and I'm going to insert for 0. I'll do that later. So I'm going to do my, actually I'm going to insert right here. I'm going to insert basically, I'm going to insert my a sub 0 at the beginning of this list. Begin at a sub 0 and 1. Sub 0. So you see here, I put this at the first. So now this is going from a sub n of 0, blah, blah, blah. So I'm going to do the same thing here, because I know that my b sub 0 is, in fact, 0 at the first position. So now I could do my c sub n's equals table of square root of a sub n I squared plus b sub n I squared. And again, you could have this all kind of done prior to the exam, or some similar type of code, even using in your problem sets, but just make sure you know how to use it. A sub n's, not my bn. Length of a sub n's. And there we go. So I've got my c sub n's. Let me do my freaks, which is equals table I times delta f. I'm going to go from I goes from 0 to 5. Now I could go ahead, oops. I'm going to actually steal a little bit of code in just a second. So transpose, I'm going to do freaks, and then cn's. Then I'm going to do a list line. I'm going to actually, now here I'm going to steal the code from our lecture 6. So let me get my fancy filling function, which I love to use. So actually, let's do list plot, and then we're going to do here, and then voila, that's our function. So our dominant frequency technically would be the 0th order harmonic, but really it's the first fundamental because that's the only one we really care about. 0th order frequency is not really an interesting one to kind of calculate. So we've calculated the harmonics. We've looked at the dominant frequencies, fundamental frequencies. Now all we have to do is look at this frequency spectrum below and figure out which of the frequencies or which of the three Fourier series corresponds to the frequency spectrum. So an inverse problem. You know I like to give these. So looking at this problem, I could immediately tell that my delta f is equal to 0.5 hertz. And thus my period is equal to 1 over 0.5, which is going to be equal to, let's pull up Mathematica. The question's not asking for it. I'm divided by 0.5. But I might ask that question a little bit later, or 0.5, excuse me. 0, so 2. So that is going to be 2 seconds. My number of harmonics here, 1, 2, 3, 4. So we're going from n to 4. N goes to 4. So now let's figure out what frequency spectrums should work. So right now I can immediately say that my A naught is equal to 20. And we know that the general function for my Fourier series is going to be A sub naught over 2 plus summation from n equals 1 to infinity. But in this case, there's only 4 harmonics, so it's not going to be infinity. It is going to be equal to 4 of A sub n times cosine of 2 pi. Now remember, this is in hertz, so this is f. So 2 pi times n times delta f times t plus b sub n sine of 2 pi n delta f t. So let's go ahead and figure out. All right, so first off, I know that this first one has to be 10. So this one's not going to work automatically. I also know that this one's not going to work automatically. So I'm sitting pretty. It's probably number 2, right? Well, let's make sure and let's double check this. So this one works. Great. So now I've got to look at what's going on here. So 0.5. So if I plug in, I know that let's look at this frequency here. So I know that this should be equal to 2 pi times n times delta f times t. T. We'll get rid of t here. So this has to equal pi. So I know here that my n, my fundamental frequency is going to be equal to 1. And my delta f is 0.5 or 1 over 2. So that's true. Okay, we've got that. So this should be 0.5. So the next one should be what? Does 3 pi work here? Or where's my 2 pi, right? Because I'm going in terms, I'm multiplying now by 2, so it should be 2 pi. Well, that makes sense, right? Because here, my A sub, actually, first, let's also double check that this works as well. So what's the value here? So I only have an A sub n, so my B sub n is 0, but my C sub n, remember, is equal to square root of an squared plus bn squared. So this works as well, right? So our frequencies match because we should expect, again, this first fundamental is going to be 2 times pi times n, which is going to be equal to 1 times my delta f. So that should be equal to 5, or actually pi. So excellent. And then again, the coefficient here has a value of 5. I don't see any signs, so again, my A sub n and C sub n, everything works out here. So my next harmonic coefficient, my A sub n and B sub n, my C sub n is 0. So if my C sub n is equal to 0, then my A sub n equals 0, my B sub n equals 0. So this is 2 essentially for the second harmonic. So that makes everything equal to 0. So again, I don't see that frequency contribution. But then if I multiply by 3 over 2, all right, now I get a value of 15. So again, this is fine here, and so this is fine for 4. So we can even look at that right here. So let's go ahead and kind of break this one down. So does our our coefficients kind of match. So our frequencies are fine, but let's look at the magnitude here. So I have a little bit of trouble with that. So here we have 5. So 5 squared is going to be 25. This is going to be 10 divided by 2 squared. So let's look at square root of 5 squared plus 10 times square root of 2 squared. Is that 15? Okay, that's looking good. What about the last one? Uh-oh, what's square root of 100 plus 100? Uh-oh, that's where it's wrong. So, beep, nope. So none of these work. So we needed this last one to have that, again, that same value, right? The C sub n to be equal to 10. But our A sub n here and our B sub n here failed. So frequency-wise, this one's perfect. A sub n over 2 is perfect. But we just had that last one. This is where it fails. It was perfect all the way up until here. Let me kind of erase it. So this is a completely valid, again, there's multiple types of Fourier series. This is just one possible one. But this is perfectly correct up to this point. But here, these coefficients is where we were let down. So that's it for problem 1. So next time we're going to do problem 2. A little bit of a hint, no pressure, just DFT. So all right, I'll see you in the next video. Thanks, and good luck.